Okay.
The floor is yours.
Thank you, Stefan, for the nice introduction. Thank you, everybody. I'm so happy that I see so many of you for almost at the end of our user meeting. And also, I would like to thank two speakers before who present also very nice things. It's Bora Derin. He showed very nice application already on aiMP and aiOQ yesterday. And another important point, if you would like to have good result from material informatics, as mentioned yesterday by Professor Kreuter, so it's important that your data will be correctly processed, that your data will be cleaned, and that your data will be also physically or thermodynamically corrected. And now let's have a deep dive in aiMP and aiOQ, and also I will show you another application of these two databases. So first of all, if we're talking about traditional CALPHAD databases, we all love them. We also have very nice talk from Philip mentioning the update on GTOx, yes, and it's very good, sustainable databases. They are accurate, they use knowledge expert, but they only cover certain temperature ranges and composition ranges. So they're very accurate in a certain limited chemical space, and the chemical space is large, yes, and we have sometimes also the spaces where we have no data, yes. Contradictory to this, we also have DFT repositories right now, yes. They have much more larger coverage for the data, yes, but the problem with such of the databases or DFT data that they're mostly giving you the knowledge about 0K. So, and in order to bridge these two databases and use them fully screening and descriptions, also considering the temperature dependence, it has been developed two databases, aiMP and aiOQ, which actually put the power of the both together, which we can use also for the high-throughput screening in order to reduce the number of compounds which need to be tested experimentally and also save our time and money for it to find really promising materials. So if we look at the numbers, so in these two different data worlds, from our side we have CALPHAD. It's very reliable databases, but it's limited amount of the compounds present in these databases. And if you also consider the data growth, it's not so big, yes, because you also need expert knowledge to grow and develop these databases, which also has been shown here in many presentations. From our side, we have DFT data, which are really large bunch of the data from one side. From our side, it's also growing much faster as a CALPHAD databases. Also, it's the difference in the covering of the temperature range in both of the cases, and same also which phases it's covered by DFT and by CALPHAD databases. So let's see how it's combined in aiMP and aiOQ together. So in this case, in order to build the thermodynamic description based on the data provided by DFT calculations, the first things what we need to do, we need actually correct the enthalpy formations. So because experimentally we usually have it at the room temperature, yes? So we need to introduce certain correction scheme which make this data thermodynamically consistent, which is very important. So in order to get good results. And this would be like the first step to do it. As soon as we have our thermodynamically consistent data, then we actually finally can apply our machine learning model. It can be any of them to get the temperature dependence for the entropy and for the heat capacity. Because if you'd like to derive the Gibbs energy, we need to know all these three components. So how the correction has been done? At first, if you would not do any correction between the DFT 0K data and compare it with experimentally, we can see that mean absolute difference would be like that, and we're probably not so happy. It also doesn't follow normal distributions as we would like to have to correctly apply machine learning, also statistically models, which also mentioned by the previous speaker. Right now, thank you that people still calling some of them statistically models. I really like it. So from our side, so MP already take care about it. Material project has some correction scheme inside, which builds on the 222 components, yes, and they already reduce this mean absolute difference to the 10.5 kilojoule per mole, which is quite nice. So the GTT comes even further and introduce our own correction scheme, which applied in aiMP, which actually also significantly reduce this mean absolute error even more. So now we have the corrected data for the formation entropy, and now we can start with machine learning modeling. How we can do it? We can use, for example, a standard pure compound database, because now the data are consistent with each other, yes? And we select, for example, for the training set, over 3,000 compounds, and consider temperature range from the room temperature till the 5,000 K, which is the classical temperature range for the CALPHAD databases, if you look on any of them. And then it was selected 12 different discrete point temperatures in such a way that we could, for each temperature range, apply separate Gaussian process. And then as soon as they have it, we all know classical CP dependency from the T, so we can then derive as output our functions, so entropy and heat capacity, also in such a way that they are consistent with each other. And if you look on the test performance of these models, so it has been tested on 48 compounds, which would not use for the training. And we can see that the entropy root mean square error is quite small, and also experimental uncertainty, we would be just quite happy. It's 1.1 joule per curl per Kelvin. And here you can see actually the application example. If you have this trained model and try to predict such a complex compound, as you can see here, natrium, aluminum, silicon, 308. So it's actually quite fantastic results, because we are very close to the discrepancy from the GTOx database. From on our side, we have some deviation from the pure substances database for the entropy dependency from the temperature. On the right picture, you can see that also quite good agreement between all the databases and the aiMP, and I think it's quite promising result. So what we get at the end? As soon as we apply our machine learning model, we have the most important component, which is important to derive the temperature dependency from the Gibbs energy, but in comparison to the standard CALPHAD databases, so it's cover much more compounds, right? So what at the end we have two databases which can exist together, which actually provide you more input and can make with scalable temperature dependency thermodynamic functions for the large compound space in the CALPHAD style. So how you can apply aiMP and aiOQ databases? There are three application cases. So first of all, what is also very important, it's data cleaning. You need to know that if your data are consistent. Even if you do the classical CALPHAD assessment, you need to know that your data have correct units, so that there's no problems in dimensionally. And if you think about pure compound databases, yes, to screen with over 3,000 compounds and manually check all this value, it would be not possible. And it's how actually aiMP and aiOQ can help you also to find inconsistency in the data and maybe just check 20 entries instead of many of them. The second application case, on which I will talk a little bit more, it's how you can use these databases for the screening of the promising materials for your certain applications, which much faster if you do it manually or experimentally. And last one, you also can use this for the phase diagram estimation and optimization, because it's also not easy, especially if you think maybe about newcomers in the community. If you're not so experienced with the CALPHAD assessment, it would be really nice to have this functionality. So let's look on the one certain applications. It's from nuclear applications. So here you can see silicon carbide composites. So inside you have the fibers, and here it's the silicon carbide matrix. And what happens with material under exposure at the temperature 1845. So we can see that it's damaged, yes. And what it's important to find the nice coating materials. It could be, for example, any metal-oxide in such a way that we can protect this part so in this application, which is very important. And if we start to think about possible compositional space, it could be quite a lot. So it can be any metal oxide in that case. And we will select it in 3 main steps. So when we specify our requirements in such a way, so we don't want to have any reaction with silicon carbides, first of all. Then we don't want have any phase transformation at a high temperature to avoid possible internal stresses, for example, if transformation could happen, or the metal, material melts way too early. It also should be no evaporation in air on the steam, so that with coatings it's not disappear from that part. And if you apply materials, informatics, and data science, actually here you can see the reduction of the possible compounds, also in percentage, if you apply this specification one by one sequentially in order to rank our candidates. So let's look exactly. So in the first step, when we apply specification number 1, no interdiffusion between silicon carbide and any metal oxides, we use the database aiMP, and then we define the condition as following. So we would like to have any metal oxides that doesn't have any reaction with silicon carbide. So they are really good candidates for us. We would like to keep them. That's why they are marked with green color in these boxes. So also we should keep and stay with possibility to maybe consider some of them that, that silicon carbide still reacts with the metal oxide, and but amount of the silicon carbide is not disappear, so it's still more than 0. And the red one, so it's we don't, we don't want to have, right? Okay, so and you already can see some big reduction what we already done in the first step. So then, on the second step, we use the pure substances database. Why? Complementary to aiMP, because aiMP does not have data on the liquid phase, and it's important. So especially if you try to evaluate melting temperature. So that's why here the classical database plays an important role. So again, if the melting temperature of a selected material is more than 2000, it's good for us, we keep it. If it's in between 1400 and 2000 K, we also can still live with it. And we also have, if the melting temperature less as we wish, we don't consider this anymore. Additionally to this, we also need to consider transformation temperature, not only the melting temperature, because we don't want that material will change the phase, so and that it can come to internal stressors, because it's also make influence on the thermal expansion and on the density. So that's why we keep some element carefully. So only in the case that solid phase transformations below 1400, or the red if it's below 2000, and it's marked in the boxes like that. So now the last condition, so we don't want that silicon carbide evaporates in steam on the air. So you can see the equation, how it's formulated. So here they keep the temperature. Again, we stay with usage of the pure substances database. And finally, we have our 13 elements, which metal oxides we are considering as a promising coatings candidate, and it has been done fast. So, and we reduce a lot of experiments what you need to perform. So, at the conclusion, I just have quite short message. I think I could impress you and show you how actually you can make bridge between the classical CALPHAD databases and DFT-based databases, aiMP and aiOQ. So we also show the application how using the high-throughput calculations, you can do screening and select some materials for the application. In this case, it was silicon composite. Yes, and yes, here you also can see the list of elements or compounds in aiOQ and aiMP in both databases. You also can find it in the documentation or in the publication of the case here. And before I finish my talk, I would like to invite all of you to participate MSc in Darmstadt. That will be this autumn. So, because of 2 reasons. First of all, I'm personally, with my colleague and friends, organizing 2 symposia on computational and experimental thermodynamics and kinetics and material, and also on the data-driven modeling and design. I will just short it, yes, so, because the title is too long. If you're interested, you still can maybe submit the poster. We will arrange with organizers because we are good contact. And also, don't miss the plenty of GTT talks. And this time, we got a lot of highlighted lecture. So I have myself keynote talk. And Please join us at MSE. We would be happy to see you if you have any questions. So contact us, and if you would like to discuss more on this topic, you can contact the expert, so Casey, Omer, and Moritz. You also can read the paper of Casey, which is really fantastic. I would recommend everybody to read it. I enjoy it a lot, and thank you very much for attention.